let's now analyze this problem that includes a mass spring system coupling as a piston to a tank. It's just one that I created really just to practice the use of couplers and especially hydraulic systems. I have another little beginning of the word graph over here, but let's focus for now on really just deriving the equations, maybe in a complete form. I haven't put a force on here, but I'm going to just put another independent force here. Okay, an input of some kind. Maybe that's a model for some magnetically driven force on here. Again, it's really just a made-up system. When I write something like this, short restriction, or when you have a short pipe here, we're assume that it really is just causing some resistance to the flow between this tank, right? So we're going to model this as an ideal tank. But the key is, it's in terms of a coupler example, is that we've got a piston here. We'll assume that we have the area of the piston that we know, the displacement of the piston x of p, and there's an ideal spring. There's probably some damping in here too. We'll throw that in there for completeness. But let's use this as an example just to directly write equations. So how do we begin? Well, I like to look at how many energy storing elements I have to begin with. We have a tank. Since this is not a long pipe, there's no inertia of the fluid that's going to be storing any significant kinetic energy. So in the hydraulic part, really you just have this tank, friction here. There's a coupler. The mass itself can store kinetic energy in the mechanical translational domain, and then we've got a spring that can store potential energy. So there's three possible states, right, that we want to focus on. Right, it's the call that x sub k is the spring deflection. The momentum of the piston mass, either we choose either p sub p or v sub p. I like to begin with momentum always. And then we've got excuse me, the volume of the tank here. Let's call that v sub t. Okay, so those are the three possible states, and as we start analyzing the relationships, we may find that, again, some of them are not states if they can be related to one another, right? And that's going to be a key part of the analysis of systems as we go forward. Here we're just going to we're working this problem in sort of a classical way. I always think that it's important to review that before we move into bond graphs. So let's begin writing equations. Okay, so let's start off with writing the equation for x sub k. What is that? X, the rate relationship from the basic definition for that spring, is that the rate of change of the spring is, well, the velocity of the spring. Now, what is the velocity of that spring? Since one side is grounded, it's moving at the same velocity of that mass for this ideal spring. So you can just write that, oh, that's the velocity of the piston. But the velocity of the piston can be related to the momentum, right? So that means that we can write x dot k either as Vp, if that's our state, or as P sub P divided by the mass of the piston, right? And that is a finished, complete equation. We'll number that number 1. So we're done with that state equation. This is tracking the displacement of the state. We probably would need to know what was the initial deflection, if any, because this is under pressure. There's some initial pressure here. This is initially deflected. We want to know what that is. That tells us how much energy is stored there initially. It would give us an initial deflection, and then we could analyze the system from there. Let's move to the momentum state, P sub P. Well, the rate relationship for that mass is the rate of change of the momentum, which is the sum or the net forces on that mass, right? You can go ahead and draw a Freebody diagram if that helps you, right? If we're defining, say, the motion positive in this direction, as this moves, it compresses the spring. We can say that that for that motion, the spring is going to cause a force pulling back against it. Over here we're going to have a force that's due to the piston acting on it, so I'm going to call it F sub P. We know that that's equal to area of the piston times some pressure at this point, right? What else? What other forces do we have? We didn't put any damping in there, but we could. Let's go ahead and say that we've got some damping, and that damping force is just, let's call it some constant B times the velocity. Since it's grounded against the piston wall, we'll say that that's also the velocity of the piston. And are there any other forces that we need to worry about? Not really, right? So let's begin trying to let's use that free body diagram to write the sum of forces here. That's going to be minus Fk, right? And this is a negative force too, so I've got the minus, and then also that as it moves, I got that Fb, yeah, that Fb in there, minus also the force of the piston. No other forces. Oh, and actually, sorry, I put in an input force, right? I forgot that I had added this F of t in here. Okay. Okay, so each one of these forces I need to get rid of, so we're going to work this explicitly here, completely here. Fk is just whatever that k is there times x of k, and we're done with that. This term is known. Fb, well, I wrote that that's Fb times Vp, and Vp we know can be related to state through the momentum relation. So that term is done. Fp we need to find. Ft is known because it's an input. So what is Fp? Well, Fp is the force on the piston, due to the piston, and that's the area of the piston times some pressure. That's the pressure in this region, right? So what is that pressure? Right? We don't know that. So how do we find that pressure? Now we've got to jump to the, to this, hydraulics region, and we know that we've got, flow coming through here. So how are we going to analyze that? I'm going to break this down. We know that as it couples into this tank over here, at the bottom of that tank we've got P at the bottom of the tank, and the nice thing is that we know that in terms of the state. So if we know the capacitance of the tank and we know the state of the tank, we can find that P sub t on this side. We've got some maybe some friction some resistance to the flow here. We need to decide how we would model that, and then we've got flow coming through here, don't we? We've got some Q, and then we've got this pressure over here that I'm calling P sub P. Okay, so, and by the way, note the momentum, I don't block it at the bottom, so make sure that you know that this is pressure here, not momentum. So this little element here is a friction resistance. Let's assume that we'll take that as a known resistance, and just to make things easy, let's just say that the pressure drop across here, let's call that delta P, is linear. Let's call that R. Let's call that a fluid friction, R sub F, times whatever that Q is here. Now what is that delta P? Well, it's going to be, that delta P is what? It's P sub P minus P at the bottom of the tank, right? So that means that we know this term, and we can find this, what is this, P sub P in terms of this pressure drop, which we would know in terms of that. So let's write that out. We can say P sub P is what, delta P plus, right, the pressure at the bottom of the tank. So note, I've started off with this term. I now have it in terms of pressure in the bottom of the tank, which I'm going to know as a function of that state. I just need to know this delta P, which I know here, and I'm going to know Q, right? Because Q is going to be related to the piston motion, right? Q is actually the flow rate from the piston, and that's actually the area of the piston times the velocity of the piston. You see that? That's the coupler relation, right? And that can be written in terms of momentum. So that's A over M times P sub P. So backing all this up, Q, RF times Q is this term. I now have delta P and PT in terms of state variables. I'm going to write all of that out here. I have A sub P. P sub P is delta P plus PT, and that's equal to what? Right, I'm going to make substitutions here, and at the end of the day I have A sub P squared over the mass of the piston times P sub P plus A sub P divided by CT VT. So you see what I've done is I've written the force due to the piston here, all in terms of two states of the system. I'm assuming that I'm going to be able to write V sub t fairly easily, and I can, because V, and by the way, that would be the second equation if you make all those back substitutions. Now over here, I'm getting kind of tight. I'm going to move that over a little bit. I can write my last state equation as V, the rate of change of the volume in the tank. That's the flow coming into the tank, which, if I look at this, it's only the flow entering through here, which is Q, and I found Q, right, in terms of AP times VP, and in fact it's all here, right? So basically V dot T is what, AP over MP times P sub P. That's my third state equation, and I'm done.